We're essentially looking at this guy. How do you calculate the work done? Well, it's a line integral of the vector field with the space curve. And we found out from this new theorem from yesterday that what you need to go hunting for is a special function called the potential function. And it has the property that its gradient is your vector field. And if you can find such a function, then all you need to do is evaluate the space curve. In other words, find its coordinates at the start, at A, and find its coordinates at the end. And that's the only two guys you need to work with, because the potential function at the end, take away the potential function at the beginning, will in fact get you the work done. And the theory says that if you have a conservative field, which you will have, then it really doesn't care how it gets from A to B, it's the same answer. So you can go in a straight line, you could do an arc, you could go halfway around the universe and pop back at the other side if you felt like it. You still end up doing the same amount of work. So here's our guy up here. Pretty straightforward polynomial. So essentially what we do is we go hunting, right? We go try and find the potential function. So we know that's what we've got. So if you do the partial derivative with respect to x, it has to be this guy, and the partial derivative with respect to y has to be that guy. Are we comfortable about that? Essentially transfers into this. Right. And now what we're really doing is trying to find who f is, and we're given two distinct equations that are going to allow us to do that. And where's my brain thought going? Think integration, essentially. Okay, so I wish I'd left enough room there, so I'm going to have to squeeze it in red, but here goes. If you integrate this function with respect to x, you will add 1 to the power and divide by the new power, plus a c. And the c here is some arbitrary function of y, because in this world, y is also considered a constant. So your plus c would be a function of y. If you then take this fella and you do it, you will get 1/3, add 1 to the power, and you will get, call it h. You get that guy. Now you have these two pieces of information, and I spoke, I think, last time I used the word combined, which may have threw people. So try to think of a better word than combined. These things are equal, and you're trying to say what function would be true in both cases. And essentially, can you see that these are the same thing? So I have got my function, my potential function, and it's simply just this. Now, pretend for a minute that this guy here had a plus y squared, or this guy here had a plus 2x squared, right? That 2x plus 2y squared and that 2x squared, they would get joined as well. Well, now that you know the potential function, we're using this particular space curve from 0 to 1. Might as well do it up here. At 0, you're going to get 0, 0, which is the origin. And the position function at 1, position vector at 1, I should say, is 1 take away 2, 1 add 2, and that gives me the point 1, negative 1, 3. So this fella, who represents the work done in this space curve traveling through this vector field, is simply just going to be the potential function at the position -1, 3, take away the potential function at the origin. And if you plug -1 and 3 in here, let's see what we get. We get 1/3, -1 cubed, 3 cubed, take away a whole load of zeros, and I get -9. Oh, good, it is the right answer. -9 evidently is allowed for the answer to the work done. Is that a kind of back to front thing? If the work done is -9, does that actually mean you gain energy rather than lose energy?
I think part of it is whether the in physics we consider work as force times displacement. So if those go in opposite directions, like your displacement is in the opposite direction of the force, it's negative work.
So it does have a meaning. It's okay to be -9.
Yeah.
Okay, I can handle that. So that must mean 0 and positive are also going to happen from time to time. Okay, that process is essentially what we're going to be doing today. We're just going to get practice at different versions, maybe more complicated ones. I don't know if they are, but maybe to you they will be. But we're going to find the potential function and use it to get the work done. I shouldn't have done that. Any questions about that one? Are we good with the first one? We're good?
Professor, can you go back? I want to see how you find the points again.
Sure. Up here?
Yes.
Right. So we're told that the space curve is from 0 to 1. So when I plug in 0 here, I get 0, 0, which is the coordinates of the start position. When I plug in 1 here, 1 cubed take away 2 gets me -1, 1 cubed plus 2 gets me 3, and that gives me the destination point. So you start at the origin and you finish at -1, 3, and that means you find the value at the destination, take away the value at the beginning.
All right.
Are we good? Okay, thank you for that question. Let's have a look at another one. This is a reminder to me, come back and do 7, but I don't want to do it right now. Okay, so let's have a vector field. Oh, this is question 9. Let's have a vector field, and it's x cubed, y cubed. And we want to know the work done in moving it from a point with the coordinates 1, 0 to the point with coordinates 2, 2. So actually in this question here, aren't we told the start and finish? We don't even need to evaluate it. Well, that's it. It's pretty cryptic. There's not an awful lot of information. So I know that this is true. And so I know that df by dx is x cubed. And that means that f will be 1/4 x to the 4 plus some arbitrary constant g of y. A little bubble around that. I also know that this fella should be y cubed. And if I integrate him, I get 1/4 y to the 4 plus some arbitrary constant x. Now, this is the first time it's happened. but it's not that uncommon for this to happen. Do you notice that this is not that? Right? This thing is not that thing. But isn't this a placeholder for him? And isn't this a placeholder for that? So when you combine them, you get Are you comfortable about how I got my potential function? Does that make sense? You know it's a quarter x to the 4 plus some function of y. You know it's 1/4 y to the 4 plus some function of x. Well, the only situation where both these can be true is in this situation. I'm not seeing a lot of happy faces here. I don't know if that's a bad sign or a good sign. Are we okay with what I just did there? We are, okay.
This makes sense.
Okay, maybe that's it. Maybe it makes so much sense you're not really going to react to it. Like I just said, 1 + 1 is 2. You're not going to shake your head and say, oh, that's hard to figure out. Okay, well, we got this guy. That's very useful thing to know. Moving on then. Define the work done. It's that guy, but we can change it. And you finish at 2, 2, and you started at 1, 0. And this is the function I'm going to be using. So put a 2 in there, you get 4, and then you get another 4. So I guess that's 8. And you put a 1 in there, and a 0 in there. You get that. So you get 31/4. They're not giving me the units of work. Is what Newton meters? Am I wrong? Is what Newton meters?
Yeah.
Okay. I'm not putting it in anyway, but you know, for the purists amongst you, you need to know the units, don't you? Could be foot pounds.
Of course, yeah.
Okay. So it would be 31/4, whatever the right units are in the context of what you were doing. And that is it. It's kind of nice, doesn't it have a kind of flow to it? You find the potential function and then you just evaluate it at the end, take away, evaluate it at the start.
Can I see that answer one more time real quick?
Sure.
Okay. Thank you.
Do 11. Odin. Nothing special. 12. They're not wowing me with the vector fields they're giving me. I'd like to see something a wee bit more oomph to it. That's got oomph to it. Good. 14. Your vector field natural log of y plus 14xy cubed. Oh, no, we'll keep going. 21 x squared y squared plus x over y. What this question gets us to do is, first we need to determine, is this a conservative field? Because you can only do what we've just done when it is a conservative field. So the earlier questions, you just told it is or you assume it is. But in this question, we're actually going to find out if it is. And I didn't read that when I got it because I saw that and I said, oh, this would be a really good one to try and find the potential function for, right? It's not just x squared y cubed, you know, it's got some meat on it. But it might not be, it might not have a real potential function because it's not conservative. And the test for conservative is this guy. Now, they call, because I'm being consistent with the book, they call this guy P, and they call this guy Q, which is totally okay. And we have defined the partial derivative of P with respect to y, and then the partial derivative of Q with respect to x. And if these two things are identical, we have a conservative field. Have we got any bets on this? Do you think it is going to be conservative? Do you think it's maybe not? What's your gut feel?
I think it will not be.
Yeah, that log is bothering me. But I've been proved wrong before. If you take this with respect to y, you get a 1 over y. If you differentiate, and we're in the differentiation world now, this guy, it's a power rule. So would you get 42 xy squared?
I have a question.
Yes.
On our last example of number 9, why didn't we differentiate from fxy of x cubed y cubed when we went to df of x?
This is the starting point. So we're saying, look, the gradient of the potential function, and the gradient of the potential function is actually that guy.
But our very top says the f of x, the big function at the very top.
Yeah.
How come when we took the df of dx, it's still x cubed and not?
Oh, there are 2
3x
f's
squared.
going on here. There's a little baby f, and there's a big capital F. And it
Okay.
sounds to me like you're confusing the two. The little f is a potential function, and it's a scalar function. It ends up being things like a quarter x to the 4 and some stuff.
Mhm.
This fella here is a vector function, so they're not even the same thing. One's a vector. So what I did right at the start is that the gradient of this unknown function that we've still to find, little f, is equal to the vector function. So what that is saying is that this fella here, I'm writing this too much down. Let's pretend I did it from start. I am saying that there's a function out there whose gradient is equal to this guy. And this function, that's what its gradient looks like. And it's equal to this guy. So my first line is matching that guy and then matching this guy. So that's what I was doing. Now you see, right now, I'm not differentiating anything. I am just matching that this thing is equal to that. And now that I've got this information, we find the f by an integration process.
Okay.
I'm not sure I've explaining that well, but that
I'm confused because now on this example we have the ln of y plus the 14x cubed is equal to
but
p
this
and
is
q.
but this is us doing something different now. We are at this point, we are not finding little f. If you notice really carefully, what we're doing here is we're testing, is it a conservative field?
Oh, okay. Okay.
And so that's a new guy in town.
Okay.
If this
Sorry,
works,
I was just confused.
Hey, I was born confused, so I know how that works.
Okay. Thank you.
So you've got this guy, and we just found it, and I'm going to find this one. And if these are equal, it's a conservative field. And if these are equal, then we will do what we've just been doing for most of the day. Let's see what this guy looks like. If you differentiate him with respect to x, you get 42xy squared. And if you differentiate him with respect to x, you get 1 over y. And I am amazed, it is a conservative field. You agree, unless I've screwed up here? Aren't both those derivatives equal to each other? My gut feeling was saying I don't think it's going to work because that log was bothering me, but evidently it does work. Well, now that I know that it is, right, F is a conservative field, let's go hunting for what is called the potential function, right? The little f of xy. And so we start with the property that the gradient of this fella is him. Maybe I should be putting this line in, which means that, oops, this guy will be this fella. Now I'll need more room than this, so I'm going to start on a new piece. If you match the x's, if you match the first position, maybe that's a better way of phrasing it, we know that this has to be true. Great. Right, so let's find f. If you know the partial derivative of f with respect to x is this expression, then to find f, we integrate with respect to x. So that's considered a constant, so you get x log y. And this is a power rule, so you add 1 to the power and divide by the new power, and I get that, plus an arbitrary constant. Now, since you're integrating with respect to x, we'll call the arbitrary constant g of y. And that's a placeholder in case there's some bits left over that we need to match up with. Now, if you look at the second piece, this guy should be equal to him. And if we integrate with respect to y, you get add 1 to the power, divide by new power, so you get 7x squared y cubed. And with respect to y, if you integrate this, you get x natural log of y, plus a constant, which we will call h of x. Now, this and this need to be equal to each other. Well, the good news is that they are. I don't have any little leftovers that I need to accommodate for, because both expressions contain the same thing. Remember in the other one, there was a quarter x to the 4, and the other one needed a quarter y to the 4. So the placeholders, as I'm calling these, were quite useful. But if both expressions are actually equal to each other, right, the same thing, then these two basically don't matter anymore. Right? They're irrelevant. Well, that would be it. Now, if this question had find the work done, we would evaluate this function at the beginning, we evaluate this function, the potential function, at the end, and if you subtract those two things, that would be the work done. But they don't ask you for that. They basically just ask for this. Are we good? Thumbs up, great. When you do these types of questions, unless they specifically go out of your way and say, check that it is a conservative field, I think we can have the assumption that it is, right? That someone else has done the check for us. Otherwise, you're just going to add a whole load of extra work that's probably not necessary. And I'm pretty sure that if it wasn't conservative, they wouldn't be asking you to get the work done using the method that we're using right now. Okay, now I said note to self. Let's do that note to self now. Let's look at question 7. Your vector field is y squared z plus 2x y squared, comma, 2xyz, comma, x y squared plus 2x squared z. This is essentially, isn't this just a grown-up version of a two-dimensional vector field? This is a three-dimensional vector field, right? There's an x, y, and z. So anywhere in 3D space, there's a 3D vector pointing somewhere, right? It's got a whole 3D world going on. Now, the curve C is given by a parametric equation. I'm just writing it this way because it makes more sense to me. Looks like that guy. Looks like that guy. And it looks like that guy. And it's going to go from t equals 0 to 1 because web-assigned people have no imagination. It could have went from 1 to 22, but they decided not to. And it's got essentially the standard question. Find the potential function, little f, and then find the work done in this curve from 0 to 1, passing through this 3D vector field. Now, we've seen how to do it when it's a two-dimensional world, right? It's the same property. It doesn't care how many dimensions are. The gradient of the potential function will be the same thing as this guy. And that makes df by dx, comma, df by dy, comma, df by dz, comma, equals, and I'm just going to call this f because I do not want to have to write all of that here. Now, you're matching up the first one with that, the second one with this, and the third one with that. So that's going to involve a little bit more work. Let's start off with the first one. This guy needs to be him. Okay, let's integrate with respect to x. What will the y squared z term be if you integrate it with respect to x?
X,
Y.
y squared z.
Agreed. Well, z would have been better, but I guess z will have to do. What would 2x what z squared get you?
X squared, Z squared.
Thank you for good proper pronunciation. Plus, right, basically it's plus a constant. When x is a variable, aren't y and z both counted as constants, right? So I'll just call this g of yz. It's basically a placeholder in case there's some bits left over. So we got our first one. F is these two guys plus perhaps some stuff that has y's and z's in it. There might be some stuff with y's and z's in it. Right now, we don't know if there is or not, but there might be. Okay, if you match up the second one, then df by dy is this fella. And if we integrate this fella with respect to y at least, I believe you get x, y squared, z, plus an arbitrary constant. And if you are integrating with y, the other two variables, x and z, go here. Are we good? Now, one more. Let's see what we have. The third one, df by dz, should be the third expression. So that's xy squared plus 2x squared z. And if we integrate this with respect to z, the xy squared becomes xy squared z. And the 2x squared, let's check that.
Can't see the
2x
bottom.
squared z. The 2x squared z. Yeah, it is 2x squared z. So the 2x squared z, this fella here, becomes, I believe, x squared z squared plus a constant. And if you're integrating with respect to z, I guess I'll call this k, you're going to have some x's and y's. Now we need the potential function. It's made up of this, it's made up of this, and it's made up of this. So we have to figure out what that's like when you put it all together. Okay. Start shooting some stuff out at me here. What will you get? Give me a term.
Squared z.
Okay, let's pause on that. Would you agree that there's an xy squared z? Great. Anything else?
X squared and Z squared.
Right. And you notice we're not adding them, we're just saying, look, you've got an x squared, z squared. Isn't that basically everything that is that's there? The others are just placeholders so that you could do what we just did. Are you comfortable with a 3D version and how you can sometimes you have to take a bit from here and a bit from there and build your Frankenstein from pieces of a body, right? Some pieces from
So
here.
then the whole function would be the xy squared z plus x squared z squared.
Correct.
Okay, for the potential function.
Correct.
Awesome.
All right. Clicking, right? Takes a few sometimes to figure out what it's up to. Right. Any questions?
What if the x squared z squared term was only in the df dx part?
Wouldn't matter, still would get counted.
Okay.
And the reason it would still get counted is, see these funny little placeholders here? They allow you to get anybody, right? So if there's only one of the three's got it, it will be one of these three guys and therefore it could be counted, right? So it's not, oh, you have to be in all three or you have to be in two of the three before you get used. You just have to be in one of the three and you're going to get used. I mean, you
so
could
to understand
Mhm.
understand this concept where it says df of dx and you have the function where it's the x squared y squared z plus x squared z squared plus the g of yz. What I put is I put a little sub x in front of that f, and then I did it for the y and the z, and then for my final for the f x comma y comma z, I said that's equal to f of sub x, f of sub y, f of sub z added together, so I could pull it, essentially make sure I pulled everything down.
Right, the notation that you're using, if I'm hearing you correct, is you're using that notation. Is that
Correct.
what you're writing down?
Yeah, for at each of them for when I solve for when I find the
So-
antiderivative.
Right, are you putting it here?
Yeah,
Don't.
Okay, I was
I
just
mean,
helping
if you want to do it and then rub it out, because the notation that you're doing is helping you do it, but it's bad notation, because what you've said when you say that is that the derivative is this, and that's not true. The derivative is not this. The original function is this. Okay, be nitpicky, but I mean, I don't care what you do to get the answer. If a certain, Robertson notation helps me get an answer, then I might use that notation. But when I physically write it down anywhere or when I explain someone, I don't, because that notation is being used for a totally different thing and it's not correct. Right, if you plug 0 in here, all right, t equals 0, we'll get our starting point. I'll call that P. 0 4, 0. And if you plug in 1, we'll get the end point. Would you get 1, 5, and 1? So now that I have the potential function, I can calculate the work done. Right. It's the potential function at 1, 5, 1. Take away the value of the potential function at 0, 4, 0. And what does that get me? That gets me 1 times 5 squared times 1 plus 1 squared times 1 squared. Take away 0. Well, who cares? Just a whole load of zeros. 25 add 1, I believe the answer is 26. So the work done in moving through this vector field with this space curve from 0 to 1, the work done will be 26 units. Now, if we had to do this Monday's method, Tuesdays as well, can you imagine how ugly the dot product of that is going to look like when all these X, Y's, and Z's are replaced by these? And remember, we still have to have the derivative of this. Well, that's not too bad. It's 1 over 2 root x, 1 and 2t, but that would be even more stuff to do. So you'd end up with this massively big polynomial with square roots and fractional powers. And then you'd evaluate it at 0 and 1. Whereas this technique is so much more elegant. It just is. It's a really cool technique. I like it. Yes.
How do we know that that field is conservative?
We don't. We have to assume that it is. And you might say, is there a test for there's a test for a two-dimensional? You see it? This is how you check, is a two-dimensional vector field conservative? If it's 3 or more dimensions, you will assume that it is. Is there a test for it? Yes. Do you want to know it? No, you do. Definitely do not want to know the test. Trust me, it's not a pretty test. Travis?
Mm-hmm.
Okay.
I'll take that for
okay, you take my word for it, right? Trust me, I'm a mathematician.
So then I have a question on the homework then for like number 7. Does it say to find the
let me show
the
you
work done?
Yeah, let's
or
show
this
you what
conservative
that
function?
question looked like.
Okay.
In that way, you can see it in all its glory. Consider this function. Here is f. Here is your curve. Find little f, which is the way they write it down, right? Find little f, and then use it to get the work done. So in my case, I've forgotten what the done number is. Pretend it's 42. It's my favorite number anyway, right? And in here, you type in, you know, x, y squared, and all the good stuff that we found. So that's how that question was phrased. Do you notice that there is no mention of prove that it is conservative field? So I was saying earlier on today, if the question doesn't ask you to go prove it, can we just assume that somebody else has proved it for us? And that's one less thing you need to do. And in a 3D case, you kind of have to, because you don't know how to prove if it is or not. Is that good? Okay, let's keep the ball rolling. Okay, I'm gonna have to do something. Time goes by so quickly in this class. Just too much fun going on. Do you know I get paid to have fun? How many jobs can you say they give me money to do stuff that you like doing? This is just fun. Right.
My current job's that way when I have to go aloft and I'm about 200 feet up in the air.
You think that's fun? Okay.
Yeah.
Okay, I can handle that.
I mean, I get to see water aerial views from as high up as I am because I'm on a boat that's in the water.
Oh yeah, that would be cool. I love the sea. Yeah, that would be cool. Right. For the time we've got left, which is about 6 minutes, instead of doing another question, let's show you what your homework looks like, because there are some phrasing that they put there that kind of threw me for a minute. So I can start here. The kind of bread and butter question, the ones we've been doing lots of, look something like 8, although there are different flavors of it, right? You're basically going to find in this question little f, and then you're going to plug these two numbers in. Now you might say, but that doesn't look like the ones that we've got. Well, when we show you tomorrow, I'll show you how you do that, but it is a bread and butter question. Now, can you see that they like the IJ notation and I don't? But isn't that basically x cubed comma y cubed, right? And we've done ones like that. And they give you a start and finish point, okay? Here is the question where you're being asked to determine, is it a conservative field? And if it is, put the answer in here. And if it's not, DNE. So for this question here, won't you do the dp, which is this guy, dy, is it equal to this fella, dx? And if it is, then you go in and get the answer. 11, you're taking this guy and you're checking, is he a conservative first? And then you're finding little f. Do you notice that there's no work done here? There's no evaluations. You just, is it a conservative? And then find the potential function, little f. Another one similar to that one. Another one similar to that one. Another one similar to that one. And here we go. Here is your potential function. Sorry, here is your vector function. We are going to find its potential function. I actually know the answer to this, so I might as well put it in. I don't know where that 4 came from. My keyboard is miles away from the desk, so I have to stretch over. So this is kind of what it would look like. I normally do this, but there's a reason. Well, didn't mean that, didn't mean that. I got some brackets. Go away. There we go. Okay, so there's your guy. Now, if you want to find the work done, have you noticed that they've called it delta FDR? Isn't that just another way of saying capital F dr? Because isn't delta F the same thing, right? They're equal. So that's a little minor hiccup. It's just notation. Up here, it was a curve y equals 2x squared, and it's going from here to here. Can you see that this would be your destination point? So you would evaluate this at 2,8, and then you would evaluate this at negative 2,8, right? Destination, takeaway, start. So that's how that one would work. And this one is very similar to the previous question we just did. Pretty standard one, nothing much here. Pretty standard. Right, we're into the work done kind of questions. And there's a 3D one to finish with. And sometimes, for whatever reason, they write delta FDR, like in here. And other times, They call it FDR, don't they? There. See? You know, those two are totally and completely interchangeable. They're not actually asking you for anything different.